In this tutorial, we'll review density and do a calculation applying our knowledge of significant figures. So we would need to remember that density is an intensive property. What does that mean? It means that the density of a substance doesn't change no matter how large a sample size of the substance we have. So suppose that we have one cube that is exactly 1 centimeter on each side. And we saw this in class. So if we have that cube, right, not a great drawing there, but you get the idea. This cube will have a volume of 1 centimeter cubed, or 1 milliliter if we filled it with water. And if this cube had a mass of exactly 1 gram, then the density would be 1 gram over 1 centimeter cubed. And we would say the density of the cube is 1 gram per centimeter cubed. That's how we express density. Let's say I took 10 of these cubes, or I had a piece of the material that was 10 times longer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You get the idea. So this guy is a much longer version of our original piece of material. If we measured the volume this time would be 10 centimeters cubed, and our mass is 10 times the original guy, which is 10 grams. So the density would be 10 grams over 10 centimeters cubed, which equals, voila, 1 gram per centimeter cubed, which is the same density as the original sample. So even though we have two entirely different sample sizes of the same material, the density is the same. That's what we mean by being an intensive property. Okay, now suppose we're going to take something brand new and we want to go in the lab and we're going to measure the density. So suppose I have a block of a material, and it's a rectangular block, and it has the dimensions of 7.42 centimeters here and 2.75 centimeters on this dimension, and then the height is 4.11 centimeters. So when I measure the volume, I have 7.42 times 2.75 times 4.11. And I do my multiplication, punch that all into my calculator, and I get 83.864 centimeters cubed. Okay, now can I use this answer as my volume of this material? Now here's where we're applying significant figures. I have 5 significant figures here. I was able to, what this is saying is I'm able to make my calculation out to the thousandths place of centimeters. But when I look at the values used to make that calculation, my original measurements were only made out to the hundredth place. Each one of them only has 3 significant figures. Therefore, to really have an honest calculation, I have to round this to 3 significant figures. So this rounds to 83.9 centimeters cubed. I cannot have a calculation that's more precise than the measurements made to make my calculation. That's really our rules for rounding with significant figures. Now how about the mass? Let's say I put this guy on a balance, and I can measure, and at a balance it measured out to the hundredths place, and I got a measurement of 111.57 grams. So now I'm ready to calculate the density. So density equals mass, and I need to 111.57 grams. What can I say? It's Saturday morning. Divided by 83.9 centimeters cubed. Okay, so when I do that calculation, I get 1.3297 grams per centimeter cubed. Again, I have 5 significant figures. And I look here in my original measurements, I do have 5 significant figures here in the mass, but I only have 3 here in the volume. I have to round my answer to 3 significant figures. I cannot have a calculation that's more precise than any of the calculations or the measurements used in the original problem here. So this is my least precise measurement of 3 sig figs, so I have to round my answer to 3 sig figs. So my density rounds to 1.33 grams per centimeter cubed. Okay, when you do calculations, put your answer in a nice neat box, and that sets it apart from your unrounded answers or the other values you used before you got to the calculation. Now suppose that we had a graduated cylinder full of water. Okay, and I realize that this is getting a little cluttered, but all right. My graduated cylinder looks like the Leaning Tower of Pisa. There we go, we filled it with water. And what I want to do is I'm going to put both of these substances in here. And suppose that this cube here, okay, I'm going to make him red. All right, so the red cube, if we put him in the graduated cylinder, what would happen to him? We have to compare his density to the density of water, and the density of water is exactly 1.0 grams per centimeter cubed at room temperature. His density is 1.33 grams per centimeter cubed. So my red substance would sink to the bottom. Okay. How about the original black cubes? They have a density equal to water, 1.0 or 1 gram per centimeter cubed. Okay. If they have the same density of water when we put them in water, they would be suspended right within the water. We call this a density column. And it's pretty cool because we can look at relative densities of materials. Where do they fall in the column? The least dense materials would be at the top. Most dense materials would be at the bottom.